So the next topic we're going to talk about is something which sounds very, very straightforward, I guess, which is counting techniques. All right, so the idea here, we've already sort of seen a little bit in class. In particular, the way that we counted all the sequential coalitions that are in a weighted voting system. That was using one of the counting techniques that we are going to go through here. All right. So it sounds like it's fairly straightforward. It turns out it can become quite complicated, as is, that's basically the theme of math. Some of it can seem straightforward, and all of a sudden it takes a sharp right turn and becomes pretty complicated. So the math, or the science, whatever you want to call it, of counting things has a fancy name. It's called combinatorics. And, you can get your PhD in combinatorics. So it's a very non-trivial subject. Here is the sort of fundamental question at the heart of combinatorics. All right, this is the question that's going to start everything for us. Let's suppose that you have two decisions to make, and you have a number of options for each one of the two decisions. Let's say that you have m options for decision 1 and n options for decision 2. How many ways can both decisions be made together? All right, so when it's phrased this way, it's maybe not the most accessible question in the world. Let's make it much simpler. All right, let's go very simple here. Let's say that we have, let's make our decisions very explicit, let's say that we want to choose an outfit, and the outfit will be comprised of a pair of pants and a shirt. And remember, we're supposed to have, if I go back up here, we're supposed to have a different number of options. M options for decision 1 and n options for decision 2. So we need to have a possibly different number of options for each. So for this first example, all right, so for example 1, let's say we have 2 of each. All right, so we have 2 pairs of pants, and we have 2 shirts to choose from. Let's call the 2 pairs of pants P1 and P2, and the 2 shirts S1 and S2. And so the question is, how many outfits can we make here, right? Because we're viewing an outfit as a decision that we have to make, right? You have 2 decisions to make. One decision is choosing the pants, and the other decision is choosing the shirt. So, let's just be systematic about how we go through this. All right, so let's say we want our first pair of pants to be the pants that we choose. From this pair of pants, we could have shirt 1 go with it, or we could have shirt 2. All right, so how many options does this give us in total? Well, pants 1, shirt 1 is one option. Pant 1, shirt 2 is another option. So this gives us 2 options. All right, this gives us 2 ways of making that decision that have the pair of pants as being pants 1. All right, now do the exact same procedure and change the only thing that we have to change, which is what happens if we start with pants 2 instead. Well, then you could have shirt 1 coupled with that, or you could have shirt 2 coupled with that, and this gives us 2 more options. All right, 2 more outfits. So, the total number of outfits is all the options from pants 1 being the pants, and all the options from pants 2 being the pants. That's 2 plus 2, which is 4 total options. All right, so again, being humans, we are always looking for patterns, right? We want to find as many patterns in as many places as possible and try to understand systems. That's one of the things that has let us evolve the way we have. So, we're trying to figure out how to get 4 from all of the information that's in red here. right? All the information about the pants, the number of pants, and the number of shirts. So one thing that you could observe is that we had 2 pairs of pants and we had 2 pairs of, two shirts, and 2 plus 2 is equal to 4. So maybe you just add the total number of things together and that works. Or it could be 2 times 2 gives you 4. All right, so right now we have really 2 possibilities for what the pattern could be. You could either add everything together, or maybe you're multiplying things together to figure out how many total options you have. So, to figure out which one it is, let's do another example. So example 2. Let's say we have maybe 3 pairs of pants and 2 shirts. All right, so we'll label the pants as P1, P2, P3, and the shirts S1 and S2 again. So now do the exact same thing, right? For pants 1, you could have shirt 1 or shirt 2. For pants 2, you could have shirt 1 or shirt 2. And for pants 3, you could have shirt 1 or shirt 2. All right, so from each one of these possibilities, we get 2 outfits from each. All right, so each pair of pants spawns 2 different outfits. There are 3 pairs of pants, so the total number of outfits that we get from this this collection of clothes is 2 plus 2 plus 2, which is 6. All right, so if you try to figure out all the ways that you can get 6 from 3 pants and 2 shirts, well, if we add them together, we would only get 5, and that's not the right number of outfits. However, if we multiply them, that does give us the right number, right? That gives us 3 times 2, which is 6. So, this leads us to our first result in the study of counting things, and it actually turns out to be the foundation on which we establish everything else that we're going to do with this idea of how to count things. So this leads us to what's called the fundamental counting principle. And it's just a summary of, it's an answer to that first question that I asked on the last page. All right, so if 2 decisions need to be made, and you have m options for decision 1 and n options for decision 2, the total number of ways of making both decisions together is just multiplying m times n. So the number of ways that you could have decided the first thing times the number of ways you could have decided the second thing. All right, so using this principle, you can very quickly answer the question of, let's call it example 3. How many outfits? All right, so what's the number of outfits that you can make from, say, 7 shirts? Shirst? No. That would be shirts. And let's say 5 pairs of pants. All right, so take a second, pause the video, work this out, and then come back. All right, so the idea here, really not overcomplicating things at all. Use the fundamental counting principle, which tells us that the total number of outfits is going to be the number of ways of deciding the shirts, which is 7, times the number of ways of deciding the pants, which is 5. 7 times 5 is 35. All right, so you have 35 different outfits. Now, of course, you could have written this out using like these very fundamental ideas of how we can list these out that we did on the last page. So, for instance, if you had your shirts listed out S1 through S7, then you could have listed out S1 gets paired with pants 1, or pants 2, or pants 3, or pants 4, or pants 5. And then you'd be doing that for all 7 of the different shirts. Each one of these green clusters gives you 5 outfits. And then there would be a different cluster of 5 outfits for every one of the 7 shirts. In other words, you'd have 7 times 5 total outfits, which is exactly what we got using the fundamental counting principle. All right, so we have seen this idea before. I didn't make it explicit that this is what we were doing, but if you recall in the voting theory section, we did 2 instances of things that were almost identical to this fundamental counting principle. One of them was the total number of sequential coalitions. We used a version of the fundamental counting principle to count those up without, actually counting them up. Basically, we were doing fancy counting. So we did that, was one of them. And another one was in this contract negotiation problem. Right, in the contract negotiations. In this problem, we were doing things like the following, right? If you go back to your notes, we had setups that looked like this, right? We would have 2 managers chosen from the 3. And then from each of these pairs of managers, we then had, in one of the instances, we were figuring out ways of choosing any 3 of the 4 workers. And so we said something like, we could have worker 1, worker 2, worker 3, or we could have worker 1, worker 2, worker 4, or we could have worker 1, worker 3, worker 4, or we could have worker 2, worker 3, worker 4. Right, and notice that just, not thinking about it too hard, just looking at it, this idea of figuring out how many pants get paired up with each shirt, and this idea of figuring out all the different ways of matching up triplets of workers with duos of managers, well, they're basically the same kind of thought process. All right, so we've already used the ideas that are underpinning what we're talking about here. We just weren't making it explicit, and we weren't saying, this is via the fundamental counting principle or anything like that. So these ideas we've already used a little bit in class.